cluster search results instantly with k-means in Python. By the end, you will have a tiny searchable pipeline that clusters documents, a query route that finds the right cluster, and a practical feel for TF IDF and k-means tuning. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Why clustering matters for search is simple. It groups similar documents so you only compare a query to a small candidate set, which cuts latency and CPU. K-means groups by minimizing distance to cluster centers, which encourages tight topical groups. The trade-off is extra index time and more memory for cluster centers and metadata. In practice, clustering can reduce the number of comparisons by several times on corpora of a few thousand documents, saving search time at query scale. Here is the intuition. TF IDF turns text into vectors that capture term importance across documents. K-means finds center vectors, so each document sits near a center. This shines when documents have clear topical themes, and it struggles when language is highly short or semantic nuance matters more than exact words. We will build a tiny corpus, vectorize it, cluster it, and route a query to the best cluster. Now we create the tiny corpus and inspect the most common words. This snippet builds a tiny corpus and shows the 3 most frequent tokens. It prepares a handful of short texts so we can see how raw words distribute across the set. The output lists the top tokens so you can verify that the corpus has sensible signal and not just stop words. This is where you validate data quality early. If the list is garbage, fix tokenization or filtering. For a larger corpus, this step is the same, but you would sample top tokens rather than printing everything to keep iteration fast. Next, we will turn that text into vector features for clustering. This snippet converts the corpus to TF IDF features and reveals sample terms. TF IDF weights terms by how unique they are to a document relative to the whole corpus, which helps common words carry less weight. The snippet shows a small feature matrix and prints example vocabulary terms so you see the mapping from words to dimensions. The adjustable parameter here is n-gram range and maximum features. Raising max features adds more terms and can improve recall at the cost of slower clustering and denser vectors. Lowering it reduces memory and speeds up k-means. Next, we will run k-means to group the TF IDF vectors. This snippet clusters TF IDF vectors with k-means and reports cluster sizes. K-means learns cluster centers and assigns each document to the nearest center, then prints how many items landed in each cluster so you can spot imbalances. The primary adjustable parameter is the number of clusters. Fewer clusters create broader groups and reduce search complexity, but may mix topics. More clusters make groups purer, but increase index size and might create tiny clusters. Watching cluster sizes helps pick a sensible number and indicates when initialization or random seed caused uneven results. Now we try finer granularity to see microclusters emerge. This snippet increases k-means granularity to show one document microclusters. By raising the cluster count to a number closer to the document count, you can observe near one-to-one mapping between documents and centers. That is useful when you want highly specific grouping or when you intend to use cluster centers as a coarse first pass for approximate nearest neighbor. The trade-off is clear. Higher cluster counts increase training time and memory for centers while reducing per query candidate size. Use this mode to diagnose whether your data naturally forms tight microtopics. Finally, we will route a user query into the pipeline and fetch top matches. This snippet routes a query to its cluster and returns the top matching texts. It converts a short search string to TF IDF, finds the nearest cluster center, and scores documents inside that cluster to return the best matches. The adjustable parameter to watch is how many top candidates you keep from the selected cluster before doing final ranking. Increasing that number improves recall but costs more scoring time. You can also change the scoring measure from simple dot product to cosine-like similarity, depending on how you normalized TF IDF earlier. Recap in 3 crisp points. What it is: a pipeline using TF IDF to vectorize text and k-means to make search faster by clustering. When to use it: when your corpus has clear topical groups and you need lower query latency. One caveat: it trades extra indexing and tuning for faster per-query work and may miss semantic matches that bag of words cannot capture. Next step: experiment with TF IDF n-grams and maximum features to see how recall and cluster purity move together. If Practical IR helps you, subscribe for short, useful videos on search and retrieval.